So today we are going to be talking about conditional probability. This is slightly different. It is on your formula sheet, conditional probability rule. So you will see it written as the probability of F, then a vertical bar E. That means the probability of F given E. So when you see this conditional, the E is something that we already know to be true. And conditional probability can kind of change things. If I wanted to know the probability that a student in this high school is in my second hour class, then it would be 13 out of however many students in our high school, right? But if I wanted to know the probability that you were in my second hour class, given that I knew you had math second hour, what changes? There's still only 13 of you in here, but am I looking at the whole school anymore? No, I'm only looking at the people that are sitting in a math class right now. So what changes is our denominator when we do our fraction. We're no longer looking at everybody because I already know something is true. I already know you have a math class second hour. So I can already exclude anybody that is not in a math class second hour. Okay, so conditional probability, we already know something is true, so it changes the overall probability. An example of this. So if I roll a 6-sided die, what's the probability of a 4? So the probability of a 4, how many 4s are on the dice? 1 out of how many sides? 6. Okay. But now let's say I'm going to roll this dice. But I know the outcome is even. So I want the probability that a 4, given, I already know that we had an even number rolled. So how many 4s are on there? Still just 1 4, but am I looking at every side of the die anymore? No, I know it was only an even. How many evens are there? 3. So the difference is the denominator. In the first one, there was no condition, so we were looking at everything. In the second one, I was only looking at your evens. So if you have a condition, that condition is your denominator. My condition was I knew there was an even, so my denominator was how many total evens were there. So we're still setting up the probability as a fraction, but you divide by your condition. So let's summarize that. So on your handout, I think your notes, it says probability of F given E on the formula sheet. So that would be the denominator is the condition. So we're only looking at the probability of E. And the top would be the probability that both things happen. The probability that it was a 4 and an even number. So you don't have to memorize this, it's on the formula sheet. What you really, really need to focus on is the denominator is your condition. So let's look at an example. Wrote that down. Okay, so let's say we have a survey. And we are going to poll 1,017 Americans and ask about their beliefs in a higher power. So we have the region, East, Midwest, Southwest, and their responses. So Part A. I want the probability that a randomly selected adult American who lives in the East believes in God. So I am asking for the probability that they believe, but what do I already know? What's the condition that I know? They are in the East. Okay. So when I have that condition, that means the only thing I'm looking at now, it's no longer out of everybody. I'm only looking at the people in the East. So ignore the rest of the table. My denominator is the number of people that live in the East. So if we add those up, 255. Okay, out of those, how many said they believed? So 204 out of 255. Gives us 0.8. Did everybody get that? Next question. What's the probability that a randomly selected adult American who believes in God lives in the East? What did I switch? How is this question different?
You're trying the East is the
Yeah, I'm trying to find the probability that they live in the East. What do I already know? They believe in God. Okay, so my denominator, now I am only looking at the people that said they believed in God. So my denominator, if we add all of those people up,
77.
and my numerator is still out of those, the ones that were also in the East. So my numerator didn't change, but my denominator did. We get 0.2592. So when you have a conditional, the denominator is your condition, and that's all you're looking at. You're no longer looking at the entire table, just a portion of it. Any questions there? Let's try another one where I don't give you a table, I give it to you in words. So in 2005, 19.1% of all murder victims were between the ages of 20 and 24. Also in 2005, 16.6% were 20 to 24-year-old males. If you're trying to write this down, I'd probably only write down the things I underlined. 19.1% were between 20 and 24. And the 16.6 were between 20 to 24-year-old males. I am asking for the probability that the victim was male, given they were 20 to 24 years old. So I like to write things out in my probability notation, just to kind of tie everything together and help you identify where on your formula sheet you might look. I'm asking for the probability of a male given person was 20 to 24 years old. So when you set this up, the denominator is your condition. What's the probability of being 20 to 24 years old? 19.1%. So I would change that to 0.191. The top, they have to be male and 20 to 24. So how many are male and 20 to 24? 16.6, so 0.166. So we get 0.8691. Okay, so what we just found, just in general, the probability of the person being a male in 20 to 24, that was only 16.6. But if I already know the person fell in that age group, there's almost an 87% chance that was a male. Okay, so we already knew the age, so then we could find the probability that they were also a male. We use these conditional probabilities when we are trying to find the probability that two events happen when they are not independent. So our multiplication rule that we used last week required independent events. If they are not independent, then we have to use the general multiplication rule. So the probability of two events happening, and still means multiply, but instead of just doing probability of E times the probability of F, it's probability of E times the probability of F given E. If they're not independent, then knowing one of them happened changed the probability of the second one. So we have to multiply by the conditional probability. One important thing that comes from this, our other multiplication rule was for independent events. If two things are independent, then the probability of one happening is the same as the probability of it happening if something else already occurred. So we've kind of talked about like mutually exclusive means the probability of both things happening is 0. In terms of independent, when it was independent, we just did the probability of E times the probability of F. So if they're independent, the probability of F is the same thing as the probability of F given E. Knowing that it's sunny today doesn't change the probability that you are in my class. Okay, so the probability that you're in my class is the same as the probability you are in my class when it's sunny outside. It doesn't change. They are not related to each other. So knowing one thing happened did not change the probability that the other occurred. All right, so now I just have some more examples for us to finish out our day. So kind of related to our last example, we're still talking about 19.1% between 20 and 24. 86.9% were male given the victim was 20 to 24. And I want the probability that a victim was a 20 to 24-year-old male. So here's what we have. The probability they are between 20 to 24 is 0.191. The probability of being a male given they are 20 to 24 is 0.869. I'm asking for the probability that we had a 20 to 24-year-old male. So basically the probability of 20 to 24 and male. That's what I'm trying to find. If you write it out like this, we can kind of see that's just our formula that we just wrote down. We just said the probability of E and F is the probability of E times the probability of F given E. So the probability of 20 to 24 and male is the probability of being 20 to 24 times the probability of being male given your 20 to 24. So all we have to do is multiply these. One 16597, so that would round up to 0.1660. Do some more. Suppose that of 100 circuits sent to a manufacturing plant, 5 are defective. The plant manager receiving the circuits randomly selects 2 and tests them. If both work, she will accept the shipment. What's the probability that the plant manager rejects it? Okay, so the only way she accepts it is if they both work. What would make her reject it? If one of them doesn't work. If the first one doesn't work and the next one does, or the first one works but the second one doesn't, or if they both don't work, right? So can we agree these are complements? So would it be easier to find the probability that they all work, or the probability that the first one doesn't, or the second one doesn't, or they both don't? Probably just be easier to find the probability that they both work. And then how would I get the probability that she rejects it from there? Complement, 1 minus. Okay. So just kind of probability of rejecting is 1 minus the probability that she accepts. So let's find the probability of accepting. In order to accept it, both of these have to work, right? So the only way she accepts is if the first one works and the second one works. What's the probability the first one works? So how many circuits do we have? 100. Out of those 100, how many of them work? 95. Okay, here's the conditional probability. I had a box of 100, 95 of them worked. If I took out one of them that worked, how many are left in my box? 99. How many of those work? 94, because I took out one of the good ones. Okay. So then if we just multiply those, so this is the probability that she accepts it. They both work. So the probability of rejecting would be 1 minus this. So there is a 9.8% chance she would reject the shipment. Does that make sense to everybody? Let's try another one kind of along those lines. So out of 3,215 people, 130 of them agreed with the bond issue. So if I took one person, what's the probability that one person agrees? $130 divided by 32.15. Okay, if two people are selected, so the first one agreeing, that's 130 out of 32.15. But if I've already talked to one person, right, you have to take out that first person agreed, so now we only have 129 other people that agree. We have one less total person to talk to. So we get 0.0016. Okay, I just wanted to illustrate how this is different than if I assumed they were independent. In this case, these people were assuming they're dependent. Once I took that person out, I couldn't talk to them. But maybe we have it set up a different way. Maybe Jocelyn and I are both going to find one of those people to talk to. Okay, so I pick a name out of the hat and I talk to that person and I throw it back in and she picks a name. Could we both have selected the same person? Yes. What would my probability be in that instance? Right. This wouldn't change. If they're independent, the probability is the same for both of us. So we could both talk to the same person. These look the same if we only go to 4 decimal places, but if we had kept more, this other one was 0.01623. This one is 0.01635, so there is a very slight change here. In general, a lot of times we might be able to tell from the scenario if things are independent or not. If we're just talking about taking people out of a sample, we will assume they are independent if the sample is less than 5% of the total population. So 5%, that's kind of our magic number. Anything less than 5% is considered unusual. If the sample is less than 5% of the entire population, we can also assume independence, if I don't tell you otherwise. Reviewing. 29 says you have to draw a tree diagram. You do not have to do that. It's totally up to you if it helps you